All right, we're over here in started Frick's engine. So this is the reflection probe component, and there isn't actually a lot in here to look at when it comes to quote the reflection probe issue with Compressonator, because it isn't actually reflection probes. It looks like it is, but it isn't. But the important thing to note is that when you bake a reflection probe on bake, you can see it here. We go through to bake async, and this does a bunch of stuff. We're still in Frick's engine. Now we're in. But so this is where the actual reflection probe gets baked. This middle part here, connector.render, this goes down to Unity, and you can see it goes down to Unity because the moment I do control click on that, we're in I reflection probe connector, and if we say go to implementation, you'll see that we're now in Unity Fruits Engine Runner. And whenever you see Fruits Engine change to Unity Fruits Engine Runner, it means that you've suddenly entered into Unity. And you'll notice that because we've got a couple of Unity specific objects here, like Game Object Reflection Probe. So then this becomes the Unity Objects Reflection Probe. So this isn't Fruits Engine Reflection Probes, this is Unity Reflection Probes. And then you can see here that we do regular, like you can like literally look up this stuff in like a Unity tutorial. We add a Unity game object, we set its parent layers and stuff, and then we go through and we do baking. So here's actually baking, and this is the stuff that Fruits just rewrote for the splitting as well. All this stuff just got rehandled. I don't know how, I haven't looked at it, but there are changes there. Things like near clip plane, far clip planes, HDR, all sorts of stuff like that. And then we get all the way down to probe.render probe. Go into render probe, please. This, we're now in Unity's actual like source code. See, we're in Unity engine.core module. So we're already out of control, I guess would be the word. Like we can't change this. So what this is illustrating is to say that the baking part of reflection probes isn't actually the problem. Like there's stuff here to change that is changing with the splitting, but there isn't anything that needs to be changed. Down here is where we do more rendering, and I think this is the finished part. Yeah, this is the finished part. So we come back out of Frick's Engine, and we're here and doing a bunch of mippy stuff. Where's the... Okay, I don't know where it is, but at some point after this renderer is finished, it will eventually cool down to our asset variant generator, which you can kind of see on the left here appearing. Our asset variant generator will eventually call what's called bitmap block compression. Bitmap block compression is the only file within Resonite that does Compressonator related stuff. So basically, this file is like our entire use of Compressonator, and yeah, it's a sizable file. It's 200 lines, but I realize I should be looking at commentary. Give me a second. No, everything you're looking at is old code. I haven't checked out the splitting, because if I check out the splitting, I won't be able to work on the reflection probes. That's basically how it works. Some of this is new, and I'll talk about it though. So you can actually see here, if you go to like, hey, how are the references to block compression? There are 3 references to block compression, and the third one is a documentation reference, so it doesn't count. But you'll see bitmap cube, which just calls bitmap block compression, or bitmap 2b, which just calls bitmap block compression. So when we eventually get here, basically on the background of Resonite running at all times, there is a list of tasks that Resonite has calculated need to happen. And one of these tasks that gets added to the queue is, please take this reflection probe that we've just made and block compress it down to BC6H. When the task manager, like asset variant task manager, picks it up and actually block compresses it, that's when the performance issue is happening. So there isn't actually any issues in reflection probes. There are with the ones I linked earlier, that A just linked, but it's actually with block compression that the problem is happening. So there were essentially, I don't want to even number because I always get the number wrong, but like there were a bunch of issues with block compression. So first of all, the problem was that we were compressing at a quality that isn't recommended. So what you can see here is I've added this. This is new. This if it's got dot blocks like this, it's new. But I'm also telling you it's new. Compressonator itself. This is Compressonator's source. Here in F quality, you'll see the value ranges between 0.0 and 1.0. BC7 and BC6 default to 0.05. Other codecs are set at 1. Setting F quality above 0 gives the fastest lower quality encoding. 1 is the slowest highest quality encoding. Default set to a low value of 0.05. So when I saw this, I'm like, hey, why are we running it at 0.6? So we're no longer running it at 0.6. You can see here, if the format is BC7 or BC6H, we run it at this constant, not this constant. And you can see here that this is 5 and 100. Resonite expresses quality metrics in a number between 0 and 100. Compressonator reflects those as a number between 0 and 1. So we keep it at like Resonite's format, which is an integer between 0 and 100, hence 5. But you'll see here, adjust quality for Compressonator, and it will multiply it by 0.01. Is this clamp the correct way around? Yes, it is. And we clamp that to minimum and maximum as well, just in case it goes out of bounds. So that was the first one. We fixed up the quality such that now we are only making BC6H and BC7 at a default quality of 0.05. I don't have the numbers to hand, but luckily Johnny Awesome, who's been talking about the GPU compression of Compressonator, does have a table which is just like perfectly timed to be used for this particular conversation point. So I will get that on screen as well. So if we go down here, all the way down to the bottom, you can see here the times it's taking to do various compressions, at least on Johnny's computer. So you can see here that Johnny just tested BC7, but you can see that BC7 at a default quality took 6 seconds, and BC7 at 0.3 quality took 58 seconds. Now, this particular GitHub issue is saying, hey, BC7 using the GPU takes less than a second, which is once again much better than 6 seconds. But this is what I was talking about, how like you can't fix everything at once. Like it would be improper like computer engineering if I were to also take on GPU texture and compression right now. That's very clearly a different unit of work. But it still shows you the numbers here. Going back over to, yeah, it's like, hey, we just fixed this thing, and this thing we've never turned on before that we don't know if it's working. Let's just throw that on top of the work. Let's just throw that on top of the work. Now, the other thing is max threads. So I added, again, a helper method for this, where we look at the max threads. And so it inputs the max threads, and this is the max threads that we get from Resonite's configuration. And it figures out, hey, are you asking for like, do you don't care? Because if you don't care, we'll return 0. And then it says like, hey, is this format expensive to compute? And if you look at the is expensive to compute, again, you could just say like, hey, BC6H or BC7 sure are expensive to compute. And again, here there's a documentation link that talks about, where and why. So there we go. We can also see here that ASDC is disabled, again, for a link for why. So at that point, if we see that it's BC6 or BC7H, we divide this by 2. And this is the number that I want to replace. I want to basically do a bunch of testing to see if this is better, or this is better, or hey, maybe just this. Not 12, 1. Maybe this is better. And I want to just figure out like which option we're going to ship. Modders are probably gonna like mod the heck out of this, but if they want to, it's a lot easier now that we've got this all split up. But right now it's divide by 2. So that was I think like 2 or 3 bugs that we fixed there. And we're not even in Compressonator source. We were giving it too many threads and we were giving it too high a quality. Now let's talk about max threads. So if we go back to where max threads comes from, max threads comes from a bunch of stuff. Yeah, that'll do. You can see max threads comes from the asset variant generator. So let's go to the asset variant generator and figure out where max threads comes from. Max threads, asset variant generator, max threads. I think this is the one. Yeah, this is the one. So this is the asset variant generator class that sort of, manages everything up here. And you can see that when we create the asset variant generator, we pass in this max threads parameter as a class parameter in the constructor. And here, this is in the fixed branch, we can see that we assign it to the class's member variable max threads. We didn't used to do that. This line was omitted. And what this meant is that this line didn't get a value. So this value was always 0. Like 0, right? If you launch this on Steam right now, this is 0. And what this meant is that when we passed it down to Compressonator, we passed down 0. And so if we go back for a second over to block compression, 0 is the automatic thread count identifier. And it means, hey, Compressonator, figure out how many threads to use yourself. Just like guess. Just guess. How many threads do you want to use, Compressonator? And what Compressonator will do is it will say, oh, well, you've got like a 16-core computer, so I'm going to use 16 threads. But like, we're running Resonite, Compressonator. I don't care. I'm using 16 threads. And that's why you would crash, right? Because your computer would be suddenly running Resonite in VR and 16 threads of Compressonator just block compressing your reflection probe. So we fixed that one up. And what you can actually see if I find where I was here, the asset variant generator is created by the asset manager. And you can see that what we do here is we already divide the max threads by 2. But this, remember, this wasn't having oh no, wait, we don't. No, we do. Oh no, that's parallelization. So we already calculate the threads here as a max between 1 and the engine's physical processor count minus 2. So on my CPU is kind of old, so it only has 8 cores. So 8 minus 2 equals 6. So we know that this max threads will be 6. But remember that when we were creating this texture generator, asset variant generator, we weren't doing this. We are now doing this. Whoops. So this is now set to 6 correctly. But if we then go down to bitmap block compression, we can say, hey, it's actually expensive to compute, so it will do max threads divide by 2, which means the end max threads that we are currently using for Compressonator is 3 on my computer. Still not in Compressonator source code right now. Still not there. We're going to keep going. If you're interested, we're going to keep going. This is like before we even touch C++, okay? We're about to touch C++. We're now going to swap projects. I don't even have the project open. Yeah, that's not like what Git's for. You know, like if I make a mistake, I just git revert and I'm fine. We're going to touch C++. You don't have a choice. This is Compressonator.net. And just for your benefit, Compressonator.net is completely open source. So you can go ahead and just take a look at everything I'm about to show you online, if you would like to. So let's go ahead and take a look at our Test Explorer here, which should populate very quickly. You can see here that if I expand these all out, there's probably a button to do it. I really don't care. By expand all, there we go. You can see here that one of the things that we needed to do, actually, let's not start here. Let's start at the entry point. So Compressonator is actually a native library, but we are calling it from .NET. So to do that, we use these things called static externs with DLL import. What this basically does is it will reach out to a random native DLL that exists on your computer, in this case Compressonator, and attempt to instruct it to do various things. In this particular case, what Freaks Engine does, we can actually show this as well, is if we go back to Freaks Engine and we go here, this line here, whoops, I just deleted. This line here, you see, convert texture. So this is the actual function that is being used to Compressonator. By the way, this also goes through each MIP. So we tell Compressonator, use 16 threads to compute up to 10 MIP levels all at once, all on the main thread. Anyway, so let's go back to Compressonator.net. So over on Compressonator.net, you'll see SDK native methods, and then we have convert texture is here. Now, convert texture takes a source texture, a destination texture, and a bunch of options. Prior to this update that I performed, it took the options as a struct. It was actually an unsafe class, which is a very particular type of struct. Let's not go there. It's not relevant. What we do now, though, is we are using native interrupt stuff that occurs, which takes the .NET managed copy of the object and creates a pointer to an unmanaged copy of the object in unmanaged memory that C++ can actually look at. We weren't doing any of this before. This is the recommended way to do it. And the reason behind this is because we need to marshal it. Now, marshalling is where we take the .NET structure of the class and we convert it as close as possible as we can into like raw memory. If we go to not baking soda, baking reflection probes. All right, here's the reflection probe issue, and if I scroll up, it'll be in here. Maybe in here. Okay, it's low. I'll find it. Don't worry. I'm getting there. I'm getting there. Yeah, here. So this shows what will be happening. And so this where are we? Structure to pointer structure. Whatchamacallit it over here? Structure to pointer. What this is doing is it's taking all of these properties here and it's marshalling them down into raw blocks of memory that you can see sort of here. And what it has to do is it has to kind of optimize it. So you can see here the first 4 bytes took up the DW size property, which is a CompD word. It's a float, so that makes sense. And then in the next block of memory, we're able to fit 3 booleans because there's enough room to do that. Each boolean is 1 byte. If you want to know why a boolean is 1 byte when it's just a bit usually, don't go there. Don't worry about it. Don't worry about it. So that's all very cool. But the problem is that we were doing that without the marshalling, so I've updated to do the marshalling. But when we were doing the marshalling, something strange was happening. And actually, if I just push this button, I'll show you what was happening. I think I still have the breakpoint set. I do. If you heard that noise, that's a plugin I have that makes things cause noise. Here is what we call a managed to native boundary. So this here is managed, so it's still in managed code. If I push this button up here, step into, we go into native code. So we're currently running in C#. So if I push this button, we go into C++. And so what you can see here is that we are asking we're asking Compressonator to compress to BC6H, and we are asking them to do it at quality 0.05. And there's a bunch of other details here, but that's the 2 prominent details that exist. So let me go ahead and push this button. And what you'll see down here is that we've got a copy of options in what's called the watch list. This lets us look at the data over time. But we've got another one, and this is the C++ version of that struct. And so what we do is we step into, and we have to go through my translation layer these days, but now we are inside native code. You can see that we're inside native code because star has started to appear. Star means pointer. You can see that native code is appearing because we've got these arrows rather than dots and mem sets and stuff like that. So you can see here that the Compressonator options come in as a pointer to the Compressonator options, which is why we needed that marshalling. I'm going to push it one more time. There we go. Now we can see that the options have come through to C++ side. They've been marshaled down. And we are compressinating to BC6H from RGB 88888, and quality should be somewhere here as well, but it's like a big struct, so I don't really know where it is. Oh, here it is. Quality 0.05. If you're wondering why there's 7 on the end of it, floating point. So what was happening here before I fixed up the marshalling was that we were coming down here, and the format that we were going to, which is dest format here. Can I go here, please? Dest format here is Jesus Christ. Here. This was coming across as a different number. It was coming across as a incorrect number. So if we go over here, what you'll see is that we have to go up from here. Yes, up from here. When we go across the native boundary, what we're meant to see is 97 or 61 in hex for BC6H, but we were seeing all of these values. We were seeing 140, 204, 25, 3, 116, 194, like just random amounts of issues. And anyone that knows C++ well, they should start seeing what was going on here, which is overflowing, or in some cases underflowing. So what was happening here was that we were packing, is the packing above here? I don't know where the packing image is. Here. We were packing this incorrectly, such that the quality, the threads, and the format were underflowing or overflowing across the marshalling boundary. And so in managed code, we were saying, hey, do BC6H compression, use one thread and do it at quality 0.05. And then it was going across the marshalling boundary, and it was, hey, do texture compression to -3 billion, do it at quality 1 million, and use 1 million threads for it. And this is where like the nature of the problem being like so rabbit holey exists, because I fixed up Resonite calling Compressonator with the incorrect thread count, but it turns out that the library Compressonator.net was calling it with the wrong thread count. Marshalling just takes the C# memory and converts it into unmanaged raw memory. And the reason we need to do that is because C#, depending on where you're running it, if you're running it in Mono or you're running it in .NET 8, .NET 9, .NET 6, it does different memory layouts. So an array, for example, won't be a C++ array. It will be what's called a C++ safe array, which is like a structure that goes on top of an array when you're using C#. And what that means is when we pass a safe array down to C++, we don't tell people that it's a C++ safe array. C++ will try and access it, although it's as though it's a regular array, and again, you'll get underflows. You can actually see an array here. AMD command set is an array. And so you'll see that the array just sort of straddles multiple block boundaries as it goes down, because it needs to, because there's a lot of data there. So we were ending up in Compressonator.net here as destination format was like 1 billion, and threads were like 1 billion, depending on which like number you put in. However, on Windows, and only on Windows, where are we? Here. These 1, 2, 3, 4, 5 properties were added to the struct. You can see here, use 3D mesh optimize. If this variable is defined in the build system, it will add these 5 values to the struct. And you can see down here that this is only enabled on Win32. Only on Win32 do we use 3D mesh optimize. So on Linux, these properties didn't exist in the struct. But if we go back to the struct in C++ land, you can see that they had stuff before, and we also have stuff after. And more importantly, after is where we have the format. And so what was happening on Linux was that we were sending across the incorrect size of struct. And you can see that here. Can I make this bigger? Sort of. I've lost it now. Up. I think it's up. Yes. No? Up, down. Sorry if you're dizzy. I'm so sorry. Okay, here it is. So on the left, you can see Linux, and on the right, you can see Windows. So on the left here, and ignore all my debugging, it's just I'm trying to fix it out. We can see that the size of the format enum is 4, which means we're taking 4 bytes to represent the compression format. And the size of compression options is 1,492 on 94 on Linux. But over here on Windows, the format is still size 4, but the size of compression options is 1511. So what this means is that we were passing 1511 bytes to Compressonator's native code on Windows, and we were passing 1.4K bytes on Linux. And so this block diagram, which I promised this block diagram was out of sync. On Linux, it was different, and on Windows, it was different. And what that meant is that Linux just suddenly started breaking. And I had to take a look and go through everything and figure it out. And I'm like, I want it to be standardized. I want everything to be standardized to heck. I want it to work the same on Linux as Windows, or I'm not happy. And the reason behind that is because the asset variant system now runs on Linux. And that was one of the bugs, that the BC6H images were taking days on Linux. And that's correct, because we were passing random numbers to the thread count. So to do that, over in Compressonator.net, we now have a whole bunch of tests. We can actually go into compression tests, and I'll show you them here. So ignore most of the sort of foundationals here, but just look at these data rows. Each of these is a test. So this test says, hey, make a BC1 image of rainbow.png at the default quality. This one here says, hey, make a BC6H image at the default BC67 quality, which is 0.05. This one here says, hey, generate a BC6H image at Resonite's BC6 quality, which is 0.6 currently. Like on Steam, it's 0.6 currently. And it goes through that code. There's a lot of stuff that it does here to validate that everything is happening correctly. You'll see things like, hey, we're asserting that everything's okay. So here's an example. Assert that the conversion process succeeded. You'll even see there's a bunch of that inside the load routine. It's like, hey, do we support the format? Does the file exist that we're loading? Can we load the file? After we do the MIPS, did the MIPS match? You know, all sorts of stuff like that. But it then goes through and it calls into Compressonator using convert MIP texture. Slightly different to convert texture, but trust me, because I've stepped through the C++ code, they end up being the same routines. So if we go over here to the test explorer, which I'll make a little bit bigger because it'll be the predominantly more, it'll be the rest of this stuff. You can see all these tests exists. This one test that the alignment between C++ land and C# land is intact. And what I mean by that is that this is our copy in .NET land of comp format, which is all the image formats that Compressonator supports. And you'll see here that we have RGB A8 is hex 10. If one day that got out of alignment and it turned into, like, I don't know, hex A, we would suddenly be telling Compressonator to do RGB A8, but Compressonator would actually do RG8S instead because the enum is out of sync. So that's what this test does. It puts in this value into Compressonator and says, like, do you recognize this value? And it says yes and comes back out. You can see BC6H here is that 6.1 value, that 197. So that's that test. We also do a test on the size of Compressonator options because we know, based on our testing, you just saw in my previous part of the video, you just saw that it was 1523. So I have enshrined that into code that it is 1523. If you add a property to Compressonator options and that number changes, you need to come back to this test and make sure that it works on Unix and Windows, or I will shoot you in the face. Because, like, let's say you added like another Boolean that would go up by 1 byte, so that would then be 1524, and that means you'd have to check, hey, does Compressonator native agree with that? So you'd have to go to Compressonator native. You'd have to run the same operation. I even talk about it here, size of Compressonator options. And if the native size of Compressonator options isn't also 1523, this bug will reoccur. And we do the same for comp format as well. And the reason behind that is on Linux, it was packing comp format down into 2 bytes, not 4 bytes, because it was told to by the optimizer of the building process for Linux. It was told to optimize comp format down into 4 bytes. I have locked it 2 bytes. I have locked it to be 4 bytes on both sides of the boundary. You can see that in actually, the source for comp format isn't found. I'm not going to open Compressonator, but the source, what we do is we take the enum. Is there an enum here I can use? Yeah, there's an enum here. So we take this enum and we say after it, we do colon, and then we do uint. Actually, I did comp uint. And what that does is it locks the enum's data type to comp uint, and comp uint is apparently not found, but I know it's up here somewhere. Yeah, comp uint is typedef unsigned int. And so that locks it to an unsigned integer, and that means the exact byte count of that format value will always be 4 in native land and now in managed land because we have a test to cover it. The lower half of the tests actually do compression, and we can just go ahead and run them. This is live, so if it fails, it's because I typed a bunch of stuff. And there you go. It's off to the races. It successfully did BC1, BC2, BC3, BC4, BC5, BC6 takes a little bit longer. You can see the times here. I can't make this view bigger, so I don't know, just lean forward at your screen. I promise I won't jump scare at all. You can see here that it took 2.7 minutes to do all of the tests. These all take like minuscule amounts of time, but then BC6H takes 34 seconds at that quality. You'll also see that when we try and do 0.6, the test harness fails that. It says, hey, alert inconclusive. BC6H and BC7 tests at higher quality than BC67 quality are disabled by default due to how long they take. They take double this time. So BC6H would take about a minute. I don't know if BC8 exists. We can actually check, right? We go here and we say comp format dot. Actually, we can't do that there because that's a syntax problem. Let's do it down here. Comp format dot, and then here are all the formats. So we can do BC, and then these are all the BCs. So we got BC6H, BC6H SF, BC7. There's no BC8. So it's just got through 6H, and it's now on to BC7. I don't know. I can regenerate them. I don't care to, and you'll see why. I'm just going to let these finish. But the point behind the way that this works, just in case you're unaware, is it does the same thing as snapshot testing. I talk about that on my YouTube channel a few months ago when I was doing asset variant test stuff. But I'm just navigating on my computer. Give me a second. Compressonator donut snapshot. Here they are. So what this test does is it takes all of these images and it runs them through Compressonator, and then it checks the result against these saved results. So all of these results here, these are all images. These are all confirmed by me to be valid BC6H or BC whatever it is images. And what we do is we binary compare them. So what happened here with all these check marks is we did a fresh copy of rainbow.png through BC1, and then we compared it binary-wise with the existing copy of our BC1 image, and we said, do these match? And they did. What that meant is that, hey, Compressonator is consistent. It consistently compresses this image to these bytes. And only is that BC1 test consistent on Windows, that BC1 test is also consistent on Linux. And what that means is I now know, and I can just push a button and it will redo it. You can go look online. GitHub Actions does all of these tests on every push now. And it says, hey, your development machine, as in Prime's computer, a GitHub Action worker that's running Windows and a GitHub Action worker that's running Linux all agree on if we take Rainbow and we put it through Compressonator at BC1 compression, it comes out and it looks like this. And what it means is, let's say someone comes through another developer, Cyro, Ryuvi, whatever, says, I'm going to mess with this code for whatever reason, fix another bug, whatever. They can fix that bug, rerun these tests, and if any of them go red, they know that they've messed something up, and they'll be able to dig into it a lot better. In some cases, they'll be able to actually like test the image as well. It comes up depending on how you've got it set up. It comes in like a diffing program. I use WinMerge. So this is WinMerge, and we can go ahead and oh wait, that was sorry for the whiteness. Sounds really wrong. It's a flash of white. So here, what we're doing in WinMerge is we're comparing Rainbow received that came from Ubuntu with Rainbow that came from Windows. This is an old comparison, so I don't know if it will work. And it says like, oh, well, here's the images side to side. Do they look the same? Hell yeah, they look the same. But what you can actually do is you can do highlights, and you'll see, ooh, there are differences. You can even do blink. There will be a little bit of flashing here. It's not that much. Oh, you have to do highlight and blink. Right? And it'll be like, oh, here's all the differences between these two images. And so what I learned there was that there are code differences in specifically BC2 and BC6H and BC7 that occur between Linux and Windows. It is natural that those should occur because the BC higher numbers, they they do a lot more maths, and so there's probably just sort of slight optimization differences on Linux and Windows that means that those differences occur. We can also go ahead and do this comparison as binary, and you'll be able to see the differences in binary data. And this is when I could see like, hey, probably don't need to fix this, right? Because the binary data is very extremely different, and it's different with a pattern, right? There's a clear pattern going on here. So if you're an expert in like binary, you could figure out why this difference is occurring. But the important part is visually, they're the same damn image, guys. Visually, they're the same damn image. It's probably dash fast maths. Yeah, it's probably something like that. I just like I don't think we need to fix it, but all I did here is I added the operating system that they were generated from to the end of the image name. So you can see here rainbow.png generated at 0.05 quality on Linux, rainbow.png generated at 0.05 quality on Windows. And those again verify that each operating system is consistent. So every Windows machine should validate to this file, and every Linux machine should validate to this file. Now, I do this in one of my videos, but you can go do this. You can do this, right? All you need is Visual Studio and these files, which you can find at compressonator.net. Take two files that you want to compare. So here is, we'll do Shanghai. Actually, let's not do Shanghai again. We'll have to do Shanghai again because the rest are like test images. So here's Shanghai at 0.05 on Windows. And then here's Shanghai at 0.6 on Windows. And we can just drag them into Visual Studio. Like I said, you can do this right now if you're interested. We're going to minimize these two. Where did they go? Oh, did I open like the wrong image? I did. Okay, I need a 0.6 Shanghai. Do we have a 0.6 Shanghai? Shanghai. Maybe we don't. I don't see a Shanghai that's a higher than 0.05. Okay, we'll do one that we you see it. It's there. It's there. Is it there? Uh middle. Squares. Ah, here. I see it. That. Okay, I already had the 0.6 open, so I need the 0.05. Shanghai 0.05. Oh, it's just above here. Here we go. 0.05. Good. It lagged. That means that there was stuff going on there. The operation could. I can't close the file, guys. I can't close this file. Maybe I'll just like undo my changes and then close it. Yay! And then what we can do here is we can say, hey, this goes here. We can close that, drag that to the left a little bit, drag it to that there, and then we've got the same images. We can actually take them out here as well in the properties pane, and you can take a look at them. So this is MIP1. You can go to MIP3. Go to MIP3 on both sides. You can zoom in. Have a look. You can go up to MIP1 on both sides. We can go into the HPC SPC logo again. So this 0.6, this 0.05. There are differences, but like I don't know if I'm just colorblind or not. Because like there's pretty much the same damn image again. I am colorblind though, so Yeah, they're not visually enough to matter. Yeah, go do this test like on the files if you want. I would love anyone in the community that wants to, for whatever reason, like I don't know why you would do this, but for whatever reason, if you want to become an expert in Compressonator, you can go ahead and do that now through Compressonator.net because of all the tests I set up. So let's now go into where are we? We're still at Compressonator.net. The last thing I want to do before we leave off, because we've been talking forever and Fedor wants to go out, is I want to go ahead and enable the 0.6 tests and run them. And you can take a look. So what we'll do here is we will comment out these two lines, which will block the blocker from blocking. I know that was a lot of words. It'll block the blocker from blocking 0.6. So what we can say is we can say, hey, race, do just those two tests. So that's BC6 rainbow. We won't stress it out with Shanghai. We'll just do rainbow. And the segment that we're doing here will end when BC6H finishes at 0.6 quality. It's doing them one at a time. I had to limit the test to be single-threaded because, again, just choosing your battles, right? I was like, okay, does Compressonator work when we run tests at single-threaded? Yes. Okay, then we don't need to run tests multi-threaded, thanks. We need to run Linux Resonite multi-threaded, of course, but we don't need to. We don't need to run the unit tests multi-threaded for now. We can stay single-threaded. So 0.05 took 32 seconds for our rainbow image, and it's now doing 0.06. I guess I should open Task Manager. Yeah, it's not even registering, and it's done. And it took not time at all. I love it when it's just like, I'm going to prove you wrong. Okay, we'll prove you wrong, computer. Do Shanghai BC7 at 0.6. Do it. I want to watch you squirm, computer. Here we go. Test host. So test host is where you'll see the load when you're running these tests. Don't worry about that. That just means like, hey, there was a difference. That was quick as well. It took 11 seconds. I assure you, like, there's something that takes these, like, makes these take forever in some circumstances. Apparently, I'm not able to reproduce it. I assure you, they take a short amount, they take a long amount of time, except when I'm live on camera and they don't. Yeah, I need to double check, like, because I put so much stuff in place to prevent 0.6 quality from happening that it probably just isn't happening. Yeah, I'll take a look at that offline. But I hate that, like, that's such a, like, what's the word, like a bad finale. But I don't have much time. I gotta walk the dog. I'll take a look. I'll make sure that we're sorting stuff out here. The Shanghai image is yeah, I really want to rename it and like select the image name. That's what I want to do. 22 by 13.4. Oh, by the way, you can if you want to, Johnny, again, if you want to, you can PR new images to this test batch as well. And I do need a few images because I've noticed this here. Actually, that's what's going on. Shanghai is not compatible with block compression. All right, one more. We're going to try this one more. Squares at 0.06. Go. Input file must exist. Oh, it's resources.squares.jpg, PNG. Not PHP, PNG. Yeah, keep the what's the word? Keep the image 16:9. Do it. There we go. Okay, so it's doing squares at 0.6. Here we go. Here. Go away. Here. No. The base texture must have width and height as a multiple of 4. That's what I need. So if you PR an image that does not have a width and height of multiple of 4, I won't accept it. The squares take at 0.05. It actually took. It was quicker. It was quicker. It was quicker at 0.6. What the hell? Yeah, I'll validate these offline. We're not gonna like continue this anyway. I hope you enjoyed that. I hope those who are technically minded found some cool stuff that they were looking at, and understood that. If you've got any questions, let me know, and go play for it as well. Compressonator is open source.